Let's try to solve this question here. So the most abundant isotope of helium has a 4,2 helium nucleus whose mass is 6.6447 times 10 to the power negative 27 kg. So when we are solving questions related to mass defect or binding energy, we always have to be very careful what kind of mass is being given to us. In this case, they already explicitly state that this is a 4,2 helium nucleus whose mass is this much. So that means by this value here represent the mass of the helium nucleus. Okay, occasionally your question will give you the mass of the atom. So the atom itself will include the electrons that is orbiting the nucleus. But occasionally in certain questions, they also give you the mass of nucleus, means that they already eliminate the mass of the electrons that are orbiting around the nucleus. So we have to be very careful whether it's a mass of atom that we are being given with, or it's a mass of nucleus that we have here. Okay, so in this case, it's a mass of nucleus. So they also say that this is a 4,2 helium nucleus. This is the most common kind of isotope that you can find for helium. So let's write down some information that we know about helium. So helium, they already write down this is 4,2. Okay, so this value 4 here represents A, which is the mass number. So in our discussion, mass number here is related to the number of nucleon. Okay, number of nucleon is just A. Okay, what's down here is Z. Z is also known as the atomic number, but in our discussion here, the atomic number, we will just think of it as the number of proton. Okay, so number of proton will be equals to Z. Okay, so you know that all the nucleons inside a nucleus are made of either protons or neutrons. So that means if you know the number of protons already, you can determine the number of neutrons just by taking the number of nucleon minus the number of proton. Because it's only proton and neutrons that make out a nucleon. So if it's not a proton, then it will be a neutron. So you know the total number of nucleon, you just minus it with the number of proton, then you get the number of neutron. Okay, so in this case, we can see that for our case here, this is a helium isotope. So the number of nucleon is equals to 4, the number of proton is equals to 2. Therefore, the number of neutron is equals to 4 minus 2, which is equals to 2. So here we have determined that this is a nucleus made of 2 protons and 2 neutrons. Okay, so once we are done with that, we can proceed to see what does the question ask for. The question asks for first the mass defect. So the mass defect is delta M. Okay, so over here you're given information of the mass of protons, neutrons, and electrons, and they are in the unit of kg. So in this case, you are going to find the mass defect in the unit of kg. Okay, in your exam, the mass of protons, neutrons, electrons, and hydrogens they are given in both the atomic mass unit and in kilogram in your constant sheet. So you are freely able to access protons, neutrons, electrons, and also hydrogen's mass in both units, kg and AMU. So there are many ways to solve the question because you have plenty of constants being given. But in this case, I'm going to restrict it to a situation where we only have the mass in kg. So we are going to determine the mass in kg first. Then afterward, we are going to convert it into atomic mass unit. Okay, so the equation that I'm going to use for binding energy, okay, I'm going to unpack it slowly. We know that the mass of separated constituents is more massive than the nucleus itself. So I can write it as mass of separated constituents, which is the protons and neutrons all separated from each other. Okay, for this situation, they are more massive. Okay, but once you form a nucleus, you release some energy to the surrounding, right? So that causes the amount of mass that the nucleus have is less than the initial separated constituents. Okay, so because it's less, then we take big minus small. Separated constituent has a larger mass. The nucleus has a smaller mass. So how do you find the separated constituent mass? By adding up all the individual masses that we have. We know that we have Z number of protons, so Z multiplied by the mass of one proton. You have n number of neutrons multiplied by the mass of one single neutron. So that gives us the mass of the separated constituents, all the individual masses. When you add up, what are their total mass when they are separated? Then you're going to minus it with the mass of the nucleus itself. Okay, so all these values can be obtained from the question. So the number of proton is 2, so this is 2. the mass of proton is 1.6727 times 10 to the power of negative 27. So that's the mass of proton. Next, you have the mass of neutron. You have 2 neutron. And then the mass of neutron is 1.6749 times 10 to the power of negative 27. So that gives you the mass of separated constituents. Everything here is a mass of separated constituents. And you're going to minus it with the mass of the helium nucleus, which is 6.6447 times 10 to the power of negative 27. Okay, so if you proceed to key this in your calculator, somehow your calculator might prompt out with an answer that is 5.05 times 10 to the power of negative 29 kg. But I'll personally suggest to maybe not write like this. Okay, I will suggest you to try to make it consistent with the mass that is given in the question. So if you look at the mass that is given in the question, it's in the exponent of that times 10 to the power negative 27. So maybe we try to write it as times 10 to the power negative 7 as well, just to keep the standard unit consistent over here, as standard form consistent. Then if you do it that way, that means you need to shift your decimal 2 times to the front, so that will cause us to have 0.0505. Okay, why do I do that? Right, is I try to keep my number of decimal place consistent. As you can see here, this is 4 decimal place, right? I try to keep the number of decimal place consistent across all the masses that I have. If you are given with masses with 5 decimal place, then you keep it consistent. The answer also, you keep it as 5 decimal place with the same standard form. If it's 6 decimal place, which is usually seen for atomic mass unit, if you have 6 decimal place, you keep your answer as 6 decimal place with the same unit as the masses being given over here. Okay, so this is mass defect calculated in the unit of kg. We still need to determine the atomic mass unit, and here we need to recall a little bit of the unit conversion that is needed when we talk about mass. So when we talk about unit conversion of mass, you have to be clear with 3 different values that are usually used to represent mass, and 3 different units used to represent mass. So one is the AMU, the atomic mass unit, and you know that it is equivalent to 1.66 times 10 to the power of 27 kg, negative 27 kg. This one is based on the definition that one atomic mass unit is 1/12 of a carbon, 1/12 the mass of a carbon 12 atom. That was the old definition. I think the new year there's a more precise definition. But yeah, last time I think most of the time we say it as 1/12 of the mass of a single carbon 12 atom. Okay, so that's how you determine the mass of 1U to be equal to this much kg. And there's another new unit that you should be learning right now, which is equivalent to 931.5 MeV over c squared. So MeV over c squared here is a new unit that you'll be learning to represent mass. Okay, if you think about it, MeV over here is mega electron volt. Mega electron volt is a representation of energy. So energy divided by c squared, if you recall the equation, energy divided by c squared, okay, that is just equals to mass, right? So you can know that this is mass. So that's why this is this whole thing here is in the unit of mass, because it's E over c squared. Okay, so that's a rough idea I'll carry. How do you get this 931.5 MeV over c squared here? You can take this mass over here, multiply by c squared. C being speed of light, 3 times 10 to the power of 8. You square it, then multiply by this mass over here. You get the energy, right? If you convert the energy into MeV, you get something called 931.5. You can try to do it yourself. Take this mass, multiply by c squared. Then you get the energy already, right? Then you convert the energy to MeV, then you get that it is 931.5. Okay, you can do it yourself. I'm not going to show it here, but right now I'm going to convert it, the unit from kg to U, atomic mass unit right now. Okay, 0.0505 times 10 to the power negative 27. To change it to atomic mass unit, what I'm going to do is I'm going to eliminate kg from the working, and I'm going to introduce the atomic mass unit instead. So we know that 1U is equal to 1.66 times 10 to the power negative 27. So if I proceed to key into my calculator, I will get an answer of 0.0304U. Okay, so this is in atomic mass unit. Okay, of course, I can still continue to change it to MeV over C square. I'm going to continue over here. So the third unit can be converted similar to what I did just now. I'm going to eliminate atomic mass unit. I'm going to introduce a new unit, MeV over C square. So I know that 1U is equal to 931.5 MeV over C square. So through this calculation, I can see that my answer is equivalent to 28.34 MeV over C square. Okay, so here it's me calculating mass defect, but in 3 different units. One is in kg, one is in atomic mass unit, one is in MeV over C square. 3 different units to represent the mass defect. Okay, afterwards I can continue to use what I've obtained here to determine binding energy, which is what's required for question number B. Question B asks for binding energy in joule and in MeV. So I'm going to show 2 different methods of getting binding energy from the mass defect. Okay, so mass defect, we know that it's related to binding energy through this equation. EB is equals to mass defect multiplied by C square. But to use this equation, right, you have to be aware of what type of unit do you have for your mass. So let's say in method 1, the mass defect that you have is in unit of kg. Let's say it's in kg. Then kg is an SI unit, right? So we are going to do it the standard way, substitute everything and get our energy in the unit of SI, which is joule. So delta M over C square, we are going to get the delta M from in the unit of kg, 0.0505. 0.0505 k times 10 to the power negative 27 kg, and we're going to multiply with C square, 3 times 10 to the power 8 square. So this allows us to determine my mass to be 4.545 times 10 to the power of negative 12 joule. Okay, so this is us calculating mass defect using the standard way and getting our answer in the SI unit. Okay, you can proceed from here to do conversion to get MeV, because you know that for energy conversion of energy conversion, unit conversion of energy, okay, I think we are quite clear. We learned about this from the previous chapter that 1 EV is equivalent to 1.60 times 10 to the power of negative 19 joule, right? So this allows us to convert between EV and joule effectively. Then 1 mega electron volt basically is just 1 EV. Then this mega here represented as times 10 to the power of 6. So if you are able to relate between joule and electron volt and mega electron volt, you should have no problem to convert this binding energy from joule to EV first, then from EV to MeV. So that is fine. But here I'm going to show another way of getting the binding energy, which is if your mass defect is in a unit of U. If your mass defect is in atomic mass unit, then what you can do is you can find binding energy as well. But to find binding energy, maybe you can convert your mass that was previously in atomic mass unit, 0.0304. You convert it from atomic mass unit to the unit MeV over C square. Okay, so we know that 1U is equal to 931.5 MeV over C square. But this whole thing here, this whole thing here, it's only for the mass defect only. Okay, so that means there's also a C square at the back, so we shouldn't forget that. We should add on a C square at the back. Why this calculation should be done this way is because all the unit will cancel out effectively, and you are able to arrive at your binding energy in the unit of MeV quite straightforwardly. Okay, you can see that the atomic mass unit will cancel out and the C square should cancel out as well. Okay, you can proceed to think about it carefully. So this is the numerator, this is denominator, this is denominator, this is numerator. So they all cancel out. So effectively, if you get 0.0304 multiplied by 91.5, you are able to get the energy in MeV. Okay, so if you calculate this, I believe you get the answer of 28.34 MeV. Okay, and if you notice, I hope you notice this, but this 28.34 MeV that you calculate from this equation here is equivalent to the 28.34 MeV C square mass defect that we have calculated for question A. So that means by if you happen to have the mass defect in MeV over C square, just multiply it by C square, then you're able to get the the binding energy in a unit of MeV. Even more straightforward than this. Okay, so here there's two methods to determine your binding energy. It depends on what type of mass defect you have. If it's in kg, do it the traditional way, get the energy in SI unit, then from there convert to electron volt, from there convert to mega electron volt. Okay, if your mass defect happens to be in atomic mass unit, convert it to be MeV over C square first. Then once you convert it to be MeV over C square, all the units will cancel out, leaving mega electron volt as the final unit. Okay, so these are two different ways to determine the binding energy, and we are able to obtain the two units that the question asked for. Next, for question C, binding energy per nucleon. This one should be quite straightforward. Binding energy per nucleon basically is just taking the binding energy divided by the number of nucleon. You know the binding energy is 28.34 already from previous question. So the number of nucleon, we also know this is a helium isotope, so there are 4 nucleon, just like what the question mentioned up here. So from here you can calculate your EB over A, and you are able to see that it is equivalent to 7.08 mega electron volt per nucleon. So in other words, it takes about 7.08 mega electron volt of energy to remove one single nucleon from its nucleus. Okay, so this value here sort of represents the stability of the nucleus. In this case, 7 is quite a high number. It ranges around 7 to 9. Those are very high value for EB over A. So in this case, you can say that this helium nucleus here is relatively more stable. Okay, so here we have determined mass defect in 3 different units. Okay, if they give you the mass, everything in kg, then you're able to get a mass defect in kg, then feel free to convert it into AMU or MeV over C square. In certain situations, it's probably more convenient to sub in your mass of proton, neutron, and mass of nucleus or atomic mass in the unit of U. Then you get answer straight away in U. That one will be more convenient, I think. Okay, then after that, we have seen that if you have mass defect in different unit, we can use different method to determine the binding energy. Just be careful with the units. Make sure if you use the second method, you can see that all the irrelevant units will cancel out, leaving mega electron volt. Okay, then lastly, EB over A, make sure you divide by the correct number of nucleon, then you're able to determine the value that represents the stability of the nucleus.